So the question is, let G be a group of order PQ and GCD of P comma Q that equal to 1 with Q less than P. If Q does not divide P minus 1, then G is a cyclic group. So this is a very important result. We prove this by Sylow third theorem. So let me prove this. By Sylow's third theorem, the number of Sylow P subgroup of G is 1 plus Kp. We use here Sylow third theorem. So the number of Sylow P subgroup of the group G is 1 plus Kp, and we know that 1 plus Kp divides Q. Why? Because we know that the number of Sylow P subgroup divides the order of the G. So given that the order of the group is PQ, and we know that 1 plus Kp, GCD of 1 plus Kp comma P that equal to 1. So 1 plus Kp divide the order of the group, that is PQ. Since GCD of 1 plus Kp and P is 1, then we can write this 1 plus Kp divides Q, only Q. Why? Because 1 plus Kp comma P, GCD of this, let me write this, 1 plus Kp comma P GCD, if we take the GCD, then it is 1. So by Sylow third theorem, we know that 1 plus Kp that divides the order of the group. So the order is PQ. Okay, but from here we see that the GCD is 1. So we can write this 1 plus Kp divides Q. Okay, so that is I write here. Okay, so so 1 plus Kp divides Q, and where K is a non-negative integer. Okay, so since 1 plus Kp divides Q, so we can write this 1 plus Kp less or equal to Q. Okay, that is Kp less or equal to Q minus 1, that is less than Q, and given that Q less than P. Okay, so this less than P. So what we get? We get that is Kp is less than P. What does it mean? It means that K less than 1, and we know that K is a non-negative integer, that is K is greater or equal to 0. So we see here K is less than 1, then only possibility for K is 0, then only possibility for K is 0. Then what do you get? Then we get that the number of Sylow P subgroup is 1. Why? Because K is 0. So if we put here 0, then NP, that is number of Sylow P subgroup, is only 1. So that is unique. So G has a unique Sylow P subgroup. Sylow P subgroup say H of order P, and H is a normal subgroup of G. Why? Because H is a unique subgroup, and we know a result that if H is a unique subgroup of G, then it is normal in G. So since H is unique, then it is normal in G. Okay. So similarly, we find the number of Sylow Q subgroup in a similar way. So now number of Sylow Q subgroup of G is 1 plus let us say TQ, where T is a non-negative integer, that is greater or equal to 0. Okay, and we know that by Sylow third theorem, we know that 1 plus TQ that divides P. Why only P? Because GCD of similar logic, GCD of 1 plus TQ and Q is equal to 1. So by Sylow third theorem we know that the number of Sylow Q subgroup divides the order of this group. So what is the order of this group? That is PQ. And but we write here that 1 plus TQ divides P. Why? Because GCD of 1 plus TQ comma Q that equal to 1. So we can write this 1 plus TQ divide Q. Why? The answer is GCD of Q comma 1 plus TQ is 1. That's why we write this. Okay, let me proceed. So 1 plus TQ divides Q. Okay, now since we know that since P is prime, then 1 plus TQ that equal to 1 or P, right? Why? Because P is prime, and we see here that 1 plus TQ divides P. P is a prime number. Okay, P is a prime number, and something that divides P. So what is the possibility of this something? This 1 or P. Why? Because P is a prime number. I think you can understand. So let me take an example. Let's say x divides P. 5. That is a prime number. Then what is the possibilities of x? X is 1 or 5, because 5 is a prime number. So by the definition of a prime number, x is 1 or 5. If x is 1, then that divides 5. If x is 5, then this also divides 5. So if a number or something that divides a prime, then the only possibility of this is 1 or P. Okay, so let me write this. So since P is a prime number, then 1 plus TQ is 1 or P, right? Why? 1 plus TQ divides P. Okay, now case 1 we take that if 1 plus TQ that equal to P, that imply TQ equal to P minus 1, that imply Q divides P minus 1. Okay, you know that. See, if N divides T, then we can write this T equal to sum NQ. Okay, see here, If n divides t, then we can write this t equal to nq, some multiple of q. So see, p minus 1 equal to t into q. So we can write this q divides p minus 1. But see here, given that q does not divide p minus 1, so which is a contradiction. So we find a contradiction. So which is a contradiction? Contradiction. Then only possibility. So see, there are two possibilities: 1 plus tq equal to 1 or p. So 1 plus tq is not equal to p. Why? Because you see here. So the only possibility 1 plus tq that equal to 1. Then the only possibility is 1 plus tq that equal to 1. Okay. So what do you see? We see that 1 plus tq that equal to 1. That is, the number of Sylow q subgroup is 1. That is unique. Then we can say that is a normal subgroup. So therefore G has unique Sylow q subgroup say T, okay, of order q, and T is normal in G, because T is unique, and we know a result that if a subgroup is unique in G, then it is normal subgroup of G. So T is normal in G. Okay. So we find two subgroup. One is H and another is T. These two subgroups are normal subgroups in G. Okay. Now order of the intersection H intersection T that equal to 1. Why? Because since, okay, let me use another color. This. So why? Since H intersection K T is a subgroup of H, and also H intersection T is a subgroup of T. This is a well known result. We know this. And by Lagrange theorem, we know that some order of a subgroup divides the order of this group. So this is a subgroup of H, and also this is a subgroup of T. Then order of this divides order of H and order of T. Okay, I think you understand why this is happening. Okay, and also we know that we just prove this GCD of order of H comma order of T that equal to 1. Then we can write this, the intersection. See here, GCD is 1, these two GCD is 1, and H intersection T divides order of H and order of T. Then what is the possibility of this order? This is 1. Okay. Now we know that order of HK that equal to order of H intersection K divided by sorry, just a second. Order of H into order of T divided by order of H intersection T. Now we know that order of H intersection T that equal to 1. Okay, and also we know that order of H equal to P and order of T equal to Q. So that is nothing but PQ. So we get that order of HK that equal to PQ. Okay, and also we know a result. See, can we say this that order of HK is a normal subgroup of G? Can we say this? The answer is yes. Why? Because see here, we know a result that see here, we prove this H is normal subgroup of G. H is normal in G and also T is normal in G. Then we know a result that then the subset HT is a subset of G. Okay, since this is normal, then we can say this HT is a normal subgroup of G. If one of them H or T normal in G, then we can say this the subgroup HT is a normal subgroup of G. And we see here that H is normal in G and also T is normal in G. So HT is normal in G. Okay. So this is a result. So basically we use here various kind of results. So I think you all understand this. So what we conclude that? We conclude that HK is normal in G. Okay, and we find the order of HK that equal to PQ. That equal to order of G. Okay, so what you can say from here that order of HK that equal to order of G and both are finite, then we can say that HK that equal to G. We can say this. Okay, now therefore by applying internal direct product, what we can say, therefore G is an internal direct product of H and T. Okay, then what you can write? We write that G equal to H cross T, that is internal direct product, that isomorphic to H external direct product to T. Okay, because we know that internal direct product and external direct product are isomorphic. So that isomorphic to ZP cross ZQ. Why? Because H is a subgroup of order P and T is also a subgroup of order Q. Both are prime. The order of H and order of T is prime. Prime implies a cyclic, and we know that every cyclic subgroup of finite order is isomorphic to ZP or ZQ. Okay, so these imply that G isomorphic to ZPQ. That implies is G is cyclic. I hope you all understand this.